Okay, Assalamu alaikum. Can you hear me?
Yes,
Okay, fine. So, how are you doing?
good, Alhamdulillah.
Okay, so we are meeting after your examination. How was your exam?
Yeah, good, Alhamdulillah. It was a lot easier than I expected.
Okay, have you received your results also?
Oh no, I haven't gone to school since because we've had our break.
Okay, when will you receive the results?
Uh, Hopefully in 2 weeks.
Okay, probably in 2 weeks. Okay, fine. So now
Yeah.
we have completed year 11 and now we are moving towards year 12, right? So we have already completed 4 chapters in the previous grade and we have 4 more, I think, right? So if I'm not wrong, we have 4 more chapters to complete in this year, right? So the first module is module 5, right? So the topic's name is equilibrium and acid reactions, right? So
Mm.
okay, so equilibrium and acid reactions. So this is coming under the branch of physical chemistry in the chemistry. For example, if you take mathematics, in mathematics we have several branches like algebra, calculus, trigonometry, likewise. So here in chemistry also we have several main branches, right? So first we call it as general chemistry. In general chemistry we study about atoms and bondings and other stuffs. And then we have inorganic chemistry. So have you studied inorganic chemistry, the reaction between
Mm,
acids and bases, those stuff?
I think so. That's part of module one, right?
Module 1, yeah, okay. So then
Yeah.
we have chemical calculations, right? So basically in chemical calculation we study about the concentration and moles. uh, Now we have two equation in chemical calculation. First one is mole is equal to mass divided by molar mass, and then the second equation will be concentration is equal to mole divided by volume. So these two equations will be used in chemical calculations, right? So we will be having a lot of questions. Basically calculations will be involving in chemical experiments. For example, let's say we have NaOH plus HCl gives you NaCl plus H2O, right? So basically we will call it as titration reaction, right? So we will take some amount of HCl in a beaker and we will titrate it with NaOH, right? NaOH. Now here we will have HCl. Now we have to measure the volume, and if we measure the volume, and then finally we will end up with NaCl solid, right? So NaCl. Then we will measure the amount of NaCl and we will be doing some calculations. So the equations that we are going to use for this purpose are these two. N is equal to mass divided by molar mass, and concentration is equal to a mole divided by volume. So are you familiar with these two equations? Have you already studied these
Yeah.
two? Okay, then
Yeah.
I'm sorry.
Yes. Right.
Okay, right. So after that we studied about gaseous state of matter, right? So now we are going to introduce something called physical chemistry. Okay, right. So let me write over here, right? So we are going to call this as physical chemistry, right? So physical chemistry means, so basically in Sri Lankan syllabus we study under the theme of physical chemistry. So this will contain two parts, part 1 and part 2, right? So the curriculum might be different but the concepts will be the same, right? So I'm going to
Yeah.
use our Sri Lankan resource books also in order to teach you these equilibrium and acid reactions, right? So part
Okay.
1 contains two topics, two units we will call. The first one is gaseous state of matter. So we studied about Avogadro law, Charles law, Boyle's law. Did you study them?
Yeah.
Okay, then we studied about an equation for ideal gases, that is PV is equal to nRT, right?
Equals enough.
Right, so this is
Yeah.
called ideal gas equation. Now in this unit also we will require this equation, right? So now we are going to transform this equation for concentration. How can we transform this ideal gas equation for concentration? Do you have any idea?
N1 C1 is equal to N2. Oh, not N1. It's V1 C1 is equal to V2 C2.
Okay, that is Charles law, Boyle's law, Avogadro law. But what I am telling is, now we are going to transform this equation to concentration. For that, what I will do is P is equal to N divided by V RT. Can I write this equation this way? I
Yeah.
have just brought this volume to the denominator of the right hand side, right? So now we know P is equal to N divided V is nothing but concentration, CRT, right? So we can transform this equation to this also, right? So sometimes we will require this equation also, right? So we will be studying some equations here in this equilibrium, right? Okay. Then we studied about energetics, right? So what did we study in energetics? I think in the 4th chapter in the previous grade we studied about Gibbs energy, entropy, enthalpy, right? So these things are coming under energetics, right? So and there we studied an important equation. Can you recall that equation?
The enthalpy one.
Okay, so delta G
the-
is
the
equal
energy
to
one.
delta H minus T into delta S. Did we study
Delta
this?
S.
Did,
Yeah.
yeah, okay. So this is another equation that we have studied in energetics. Okay. Now we are going to move to the part 2 of physical chemistry, right? So this is called part 2 of physical chemistry. Part 2. So in part 2 we have mainly 3 units, right? So okay, so I have just gone through your modules and other stuff. So here we are going to only study the second unit only, right? So I don't think the third and okay, for example, first and third units are included. Anyhow, we will try to study them as well if we have time, right? So the first one is chemical kinetics. What is that? Chemical kinetics. Then we have equilibrium. That is what we are going to study in this chapter 5 or module 5, equilibrium, right? And then we have something called electrochemistry. I think we have already introduced electrochemistry in the previous chapter also. I think in the 3rd chapter we have studied about cells and the potential EMF and those stuff.
Yeah.
Okay, so electrochemistry will be the extension of that unit, right? So if you have time, we will study this also. Sometimes this might be useful when you go to higher grades, right? So I mean, so after finishing your grade level, will you go to campus, right?
Sorry?
So after completing your grade
After
level, I
11.
mean, I'm sorry.
You mean year 12?
Yeah, after completing your grade 12, so after that your tertiary education will begin.
Yeah, so uni.
So you will probably go to university, right?
Yeah.
Okay, so what field do you wish to follow?
Right now, medicine.
Right now, medicine. Okay, so you don't take biology as a main subject in A level. This is basically A level, right?
Cool, but yeah, I don't.
Okay, so without taking biology, you can even go to medical faculty.
Yeah.
Okay, that's fine. But in Sri Lanka, if you don't take even physics, we cannot enter medical faculties, right? So,
Yeah, I heard that. Yeah.
okay. So you are blessed, right? So in A level, we have to take compulsorily 3 subjects: chemistry, biology, and physics, right? So sometimes if the student struggles with physics, sometimes because it involves a lot of mathematics, right? So physics involves a lot of mathematics. So if the biological science student struggles with physics, he has an option. He can take agriculture instead of physics, but he cannot enter medical faculty. Likewise, if you study, if you want to pursue engineering, if you don't take chemistry, because for most of the physical science students, most of the students coming from mathematics background, they consider chemistry as a complex subject. So they have another option. They might take ICT, information technology, but they can't go to engineering faculty. So there are some restrictions in our country, right? So you are originally from Sri Lanka. You were born in Sri Lanka or in Australia?
Dubai though.
I'm sorry.
I was born in Sri Lanka, but I went to Dubai when I was only like 2 or 3 months old, and then,
Okay, okay,
and then I came to Australia.
okay.
Yeah.
Right. So what I was telling is chemical kinetics, equilibrium, and electrochemistry, right? So now after completing this equilibrium, and then we have organic chemistry. After completing these two main units, we will come to this electrochemistry also, where we will study about cells and electrolysis. Mainly, we will talking about electrolysis, right? So have you already studied electrolysis?
No, I don't think so.
Okay, so we will study, right? So now we are going to focus on this one, equilibrium, right? So equilibrium has three main parts, right? So first one is chemical equilibrium. Chemical equilibrium. After that we have phase equilibrium. Phase equilibrium. And then we have ionic equilibrium also, right? Ionic equilibrium. So now what we are going to interested in this chapter, module 5, is chemical equilibrium and ionic equilibrium, right? But we will not be focusing on phase equilibrium because the components are not given here, right? Okay, so we will be focusing on chemical equilibrium and ionic equilibrium only, right? So before that, before we come to chemical equilibrium, we should have some understanding about chemical kinetics as well, right? So now chemical kinetics, what do you understand by the term chemical kinetics?
I'm not sure. Is that like the way chemical reactions change?
Okay. Right. So chemical equilibrium means, now we have already studied in energetics in the previous chapter. We will predict whether a chemical equation will happen spontaneously or not depending on the sign of delta G. So can you just recall it? If delta G is less than 0, if delta G is less than 0, what will happen?
It's spontaneous.
It will happen spontaneously. But if delta G is greater than 0, what will happen?
It is non-spontaneous.
It will not happen spontaneously, but when we alter the temperature, we can make it happen spontaneously. But we have another case also. We studied if delta G is equal to 0, then I told you something. I told you the equation will be in equilibrium, right? So did I tell you like that?
Yeah.
Reaction will be in equilibrium, right? So now we are going to connect this module 3 with this module 5, right? So now here we have introduced the term equilibrium, right? So what is equilibrium? Equilibrium means kind of balance. Can you understand that? Balance?
Yeah.
Balance, right? Okay. Now in chemistry we mostly deal with chemical equations, right? So when we write a chemical equation, we will be having three components. One is reactant, and we will be having aroma, and we will be having products, right? Products. But sometimes you might have encountered chemical reactions with double aroma like this. Have you seen any chemical equation? Yeah. Have you seen?
It's reversible, right?
Reversible. And okay, so these are called equilibrium reactions, right? So now here we will be having reactants and products. Reactant and products. So what does it mean? Here this is called irreversible reactions. They are called irreversible reactions. Irreversible reactions. Now these are called reversible reactions, right? Reversible reactions.
Mm.
So
Yeah.
I told you we have something called chemical kinetics. In chemical kinetics, we mainly talk about these irreversible reactions, right? So now we have there we have an equation, but this equation is not included in this chapter. But anyhow, I am introducing it to you, right? So here we will be talking about something called rate of reaction. Rate of reaction, right? So what is rate of reaction? What is rate of
Uh,
reaction?
how fast a reaction occurs.
Yeah, how fast the reaction occurs. So basically the rate of reaction is determined using the equation change divided by time. So in a specific time, how much of change is happening in a chemical reaction. For example, let's say we have A plus B and A plus B react together to give C, right? So now what I'm going to do is I'm going to plot a graph for concentration of the reactants and the products with time, right? So now here you see the, okay, now if I consider only monoatomic or only one single reactant, right? So let's say A, now I will just take this generic equation. A gives you B, right? So A becomes B in a chemical equation, right? So A is the reactant and B is the product. A is becoming B in a chemical reaction, right? So now what will happen here in the system? Initially we have A, right? So what is the concentration of A at time is equal to T? That will be higher, right? Now A is becoming B, right? So but at time is equal to T, do we have any B in the system?
Mm.
Okay, now this is the what, okay, now if I take for example, if I have NaOH plus HCl
Yeah.
becomes NaCl plus H2O, right? So now what I am going to do, I am going to take a beaker and I am going to mix NaOH and HCl, right? Now I am going to take a specific concentration of NaOH and specific concentration of HCl. Do we have NaCl and H2O at the beginning of the reaction?
No, we don't.
No, we don't have, right? So NaOH and HCl are going to become NaCl and H2O. So here I am going to draw the concentration change using this purple color, right? So what will happen to the concentration of NaOH and HCl with time?
It will. So NaOH and HCl will decrease.
Will decrease,
NaCl and HCl
and
will
ultimately what will happen?
Yeah.
They will become zero. So ultimately
Yeah.
they will become zero. Now I am going to use a different color for drawing the concentration change of this B, right? So what will happen to B? Now from 0, the concentration is 0 at the beginning, and the concentration of B will gradually increase over time, right? And ultimately it will attain a specific value, right? It will attain a specific value. So this is the concentration versus time graph for irreversible reaction. Irreversible reaction. Can you
Yeah,
understand
sure.
this? Okay. So now we will be plotting two types of graph. One is concentration time graph and the other one is rate time graph. Okay, right. Now here I am going to take a different equation, but that is what you call irreversible reaction. Now again, let's say A and B are in equilibrium. So if I want to conceptually explain this to you, now I will just take an example. Okay, right. So now let's say we have two cities, right? So we have two cities, city A and city B. City A and city B. Now this city A and city B are connected with a highway, right? With a highway. Now here let's say we have 1,000 cars, but in city B, let's assume like this, right? So in city A we have 1,000 cars, but in city B we do not have any car. So what will happen? So cars will be traveling from city A to city B. So this is called irreversible reaction. So we will consider city A as reactants and city B as products, right? So from the reactants, products will be coming. And the main point that you should notice is in an irreversible reaction. So I am talking about irreversible reaction. Irreversible reactions can be performed back, which means now let's say we have NaOH and HCl. So once you have mixed NaOH and HCl, it will produce NaCl and H2O. But if you now after NaCl is formed, this reaction cannot happen in backward direction. This reaction cannot happen in backward direction. But in irreversible reaction, both direction will be possible, which means A can give you B and B can give you A. That's why we are using double arrow mark, right? So A can give you B and B can give you A, right? So this is the differences between irreversible reaction and reversible reaction. Now I told you, let's assume we have 1,000 cars in city A and 1,000 cars in city B. So what will happen? Let's say in per hour 10 cars are moving from city A to city B, right? So this is an example for irreversible reaction. Have you understood this? Okay. Now the same thing, but here in city B, let's say we have 2,000 cars. Now what will happen? So the cars can be traveling from city A to city B and city B to city A, right? So we are going to understand the concept equilibrium, right? So equilibrium means, now you see we have something called forward reaction rate and backward reaction rate, RF and RB, right? So this is forward reaction rate and this is called backward reaction rate. So which means, what is reaction rate? So now if you have something like this, A to B, right? So now if I draw a diagram for rate and time, now for this type of irreversible reaction, now this will be something like this, right? So if I draw, now this is now did you study this equation? R is equal to product power n K1. Okay, so you didn't study chemical kinetics, right? Now assume this, right? So what is happening to the concentration of A? What is happening to the concentration of A?
Decreases over time.
What is happening to the concentration of A?
Decreases.
Is it increasing? Decreasing, right? Because A is being converted to B. So with time the concentration of A will be reducing, and with time the concentration of B will be increasing. So if I draw a rate, the rate is equal to what? Rate is equal to change divided by time. This is what I told you, right? So change is what? Change is occurring in concentration, right? So change is negative, right? So the change is negative. So we will say the rate will be reducing. So this is how it will appear, right? So the rate is reducing, right? So the rate is negative. The change is negative means the rate is negative. But what is the rate of B? But rate of B will be increasing, right? But we don't need to sketch graph for this type. I will tell you, with this idea we will draw a graph for this rate time change for reversible reaction. Okay, now listen, right? So let's say this is time and this is what, rate, right? Now you see at equilibrium Rf is equal to Rb, which means forward rate of reaction, forward rate is equal to backward rate. Now if 10 cars are going from city A to city B, 10 cars should be coming from city B to city A. So the 10 cars are traveling from city A to city B in 1 hour, right? So we have to specify the time also. In 1 hour, let's assume 10 cars are averagely traveling from city A to city B. At the same time, 10 cars are coming from city B to city A also. Now, will the number of cars in city A and city B change?
No.
Did you understand my question? Now 10
Yeah,
cars.
it won't.
No, it won't change, right? Because 10 is leaving and 10 is being added. So the total number of cars in city A and city B will be constant. They will
same.
not change. But the traveling is happening, right? The traveling is happening. So we say in reversible reaction, what will happen? Now this is A to B, right? Okay. Now right, so let's say this is the initial rate, this is the initial rate of A, and let's say this is the initial rate of B, right? So this is the initial rate of A, okay, and this is the initial rate of B, right? So what will happen to the forward direction? It will gradually reduce, but the rate of B will be increasing. Why? Because B is being formed, right? The products are being formed.
Yeah.
So the concentration will be increasing. So if the concentration is increasing, what will happen to the rate? Because rate is equal to concentration change divided by time. So if concentration is increasing, the rate also will be increasing. Isn't that so? Yeah. So at equilibrium, Rf will become Rb, which means here they should meet at a specific point. Here it should meet at a specific point. So this is the rate versus time graph for the reversible reaction. So here what you should understand is the concentration or the rate of the products will be increasing and the rate of the reactants will be decreasing, but at equilibrium forward rate will be equal to backward rate, and here it will be the rate profile will appear like this. This is called rate profile. So have you understood? Equilibrium, at equilibrium forward reaction rate is equal to backward reaction rate. Okay.
Yeah.
Right. Now you see this here for okay, so I will give you around 5 minutes time. If you want to mark anything down here, you can do it. So do you want to mark anything here?
Give me a sec. Yeah, I'm not.
So these are the things. Okay, now tell me, should I give you notes like dictating, like should I give you notes by dictating the sentences and all, or should I just explain? Is it enough for you? Should I give you
It would probably save some time if you gave the notes. So
so I can just give you some time to take your own notes, yeah?
if you have notes, like I could just use them, but if not, yeah, I'll just take the notes. I don't mind either.
Okay, then fine. Right. So now we will be moving to, what do you call, here we have to study equilibrium concept, Lee-Chittier principle, and KEQK, right? Okay. Right. So now we have seen the rate profile for irreversible reversible reaction, right? Now we will see
Yeah.
how concentration profile will look like for reversible reaction, right? So now concentration time. So what will happen to the concentration? So after it has attained the equilibrium, so this is called dynamic equilibrium. What do you call dynamic equilibrium?
Dynamic equilibrium
And
is when
static
it's
equilibrium,
attained.
right? Static equilibrium, right? So dynamic equilibrium means after, okay, so for example, it is at a stable state but still there is a motion. But static equilibrium means an equilibrium occurring at a stationary state, right? So the system is not moving, but here in dynamic equilibrium the system is moving but is still in the equilibrium state, in the stable state, right? For example, let's say if a car is moving at a constant speed, so the forces acting, the net force acting on the object is 0, right? But still the car is in motion. But let's say we have a car, right? So we have a car, okay, let's say we have an object. Now we pull the object from the both side with an equal force. Let's say we have 10 Newton and 10 Newton. But this car or this object is not moving, right? So this object is not moving. Let's say V is equal to 0. So this is called static equilibrium. What do you call this?
Static equilibrium. Where it doesn't
Static
move at all.
equilibrium means the object is in stationary state. But dynamic equilibrium means, now let's consider a car going with a constant speed, right? So it is going, let's say V is equal to 10 ms minus 1, right? So the net force is equal to 0. So if the if the car is moving at a constant speed, what is the acceleration? Acceleration is 0, right?
Yeah.
Right. So if the acceleration is 0, net force acting on the car is 0, right? So F net is equal to 0. So this is called dynamic equilibrium with respect to force, right? The net force is 0, but still the car is moving. So likewise here you see what is happening. The net force or the net number of cars moving from city A to B is 0, because why? In this direction 10, in this direction 10, but still the cars are moving, right? Can you understand that? Can you just imagine this scenario?
Yeah.
Okay, so this is called dynamic equilibrium, and the main point that you should know is a dynamic equilibrium, RF is equal to RB. RF is equal to RB, right? So now we will see the concentration time profile for irreversible reaction, right? Okay, so here it might take different patterns. Now what will happen? Now I'm just considering this equation, A becomes B, right? So here, after it has attained equilibrium, the concentration of A will be equal, the concentration of A, now after attaining equilibrium, is the concentration of A and concentration of B same?
Yes.
Yeah, it may be same, but sometimes it may not be, right? But the main thing is, so at equilibrium, RF is equal to RB, which means forward reaction rate will be equal to backward reaction rate. But the concentration of the reactants and the concentration of the products will be constant, they will not be changing, but we cannot tell whether they will be equal or not. Sometimes they might be equal, but sometimes they might be not equal, but it will attain a specific value. It will attain a specific value. For example, let's say we have A and B, right? So what will happen to the concentration of B? It will be increasing, right? So if it will be increasing and it will reach this point. So after, so this is concentration time graph. This is also we are going to draw concentration time graph. Here also we are going to draw concentration time graph. Okay, right? So here you can see the graph is going curve and then it is becoming horizontal, right? So at the point at which the graph becomes horizontal, it is called equilibrium state, right? So here this is becoming horizontal, right? Here it is becoming horizontal. So the region right to this dot line will be called equilibrium stage, right? So this is what equilibrium stage, right? So now what will happen? The concentration of A will be reducing, and when it reaches equilibrium state, the concentration of A will not be changing. It will not be changing, right? Can you see this?
Yeah.
Right? Okay. See, likewise, here sometimes it might look like this also. What will happen to the concentration of A? It will be increasing, and at equilibrium state, what will happen? At equilibrium state, it will not be changing anymore. It will not be changing anymore. So the pattern will become horizontal, right? Now this is for A. No, sorry. This is for B and this is for A, right? So the product concentration will be increasing and the reactants concentration will be decreasing. Now here what is happening? This is for B, right? Because from 0 the concentration of the products will be increasing, and when it reaches equilibrium it will become constant, right? Now here this is for A, right? So I am going to draw it for A. So what will happen? It will be decreasing, and at equilibrium, after equilibrium, it will not be changing. So here you see the concentration of A in the first diagram. The concentration of the reactants is higher than that of products, right? But here the concentration of the products is high than reactants, right? Sometimes they both might be equal as well. Right? So after equilibrium, but we have only one type of RT graph, right? So this is rate profile. The rate profile will be something like this. It cannot be like this and like this. Why? Because at equilibrium, forward reaction rate and backward reaction rate should be equal. But the concentration becomes constant, or it attains a specific or highest value, but they don't need to be equal. Can you understand that? Right? So we have studied two types of profiles. One is concentration time and rate time, right? So the rate time will be taking only one pattern, but for this we have different types, concentration and time, right? So okay, so I will give you 2 minutes time. You can just reflect what we have studied so far. So here you can see this point. So after this region, what will happen? Equilibrium, right? So after this we have equilibrium. Here RF is equal to RB, and
Hello?
Yeah, okay. So here RF is equal to RB, and what can you tell here? Here this is the concentration of reactants, right? So the concentration of reactant, this is concentration of reactant, and here concentration of product, right? So in this type of graph, what can you tell? Concentration of reactant is higher than concentration of product, right? So I am just using the first letter of reactant and product, right? So basically we
Yeah.
can denote concentration using brackets, right? So this is basically bracket. For example, if I write like this, square bracket of NaOH, what does it mean? This means the concentration of NaOH, right? So here if I write like this in chemistry, this is just a notation. If I write like this, reactant, what does it mean? This means concentration,
Concentration of the reactant.
yeah, concentration of reactants.
Yeah.
Right. Now here this is the concentration of product, and here this is the concentration of reactant. So you can tell here
Yes, yes.
concentration of product is higher than concentration of reactant. But here concentration
Yes.
of product is equal to concentration of reactant. So this might be in three situations, but here always at equilibrium RF is equal to RB. Right. So these points you should bear in mind. Okay. Right.
Okay.
Now we are going to analyze the equilibrium in two methods. One is qualitative analysis and quantitative analysis, right? So
Mm-hmm.
I'm sorry,
Yeah, I said yeah.
your voice is buffering.
I said yes.
Okay, then fine.
Yeah.
Okay. Right. So some factors might affect this chemical equilibrium. They are concentration may affect, temperature may affect, and pressure, right? So if you want, you can write this down as a note, right? So the following factors might affect the equilibrium of a reaction, right? So the first one is concentration of reactants and products, right? Concentration. There are three factors that can affect the equilibrium of a reaction. First one is concentration, the second one is temperature, and the other one is pressure, right? So these three factors can affect the equilibrium. Now for example, let's say we have an equilibrium reaction. So have you studied the contact process of sulfuric acid production?
No.
So sulfuric acid can be produced using the contact method, right? So the second step of this process is SO2 plus O2 becomes SO3, right? So this is an equilibrium reaction. So now what we will do is, in this process we will increase the temperature to produce more SO3. So since this is an exothermic reaction, right? So we will study how now we are going to analyze quantitatively and qualitatively how the reaction will proceed, right? So just note this down: concentration, temperature, and pressure, right? Now we are going to analyze how these factors will affect our equilibrium quantitatively and qualitatively, right? So quantitative analysis, first we will study qualitative analysis, and then we will study quantitative analysis.
Okay.
Right. So in quantitative analysis, we will study Le Chatelier's principle, right? So
Yeah.
Le Chatelier's principle. And here in quantitative analysis, we will be learning about Kc and Kp, right? Kc and Kp. These are called equilibrium constant. These are called equilibrium constant, right? So here we have two types of equilibrium constants. Now this subscript C stands for concentration. So this equilibrium constant, the first equilibrium constant, is associated with concentration, which means in the equation of this equilibrium constant we will be having the concentration of reactants and products. And here the second equilibrium constant is associated with pressure, partial pressure. So you know partial pressure?
No.
Okay, for example, let's say a pressure can be exerted by what? Gases, right? For example, let's say we have A gas and B gas in the container, right? So A gas will exert some pressure and B gas will exert some pressure. So total pressure PT is equal to PA plus PB, right? So the pressure exerted by the gas A is called the partial pressure of A, and the pressure exerted by the component B is called partial pressure of B. Okay, and the total will be the sum of these two partial fraction. Now if I have three gases, so the total pressure will be the sum of the partial pressure of all these three gases, right? So for example, if you have n number of gases, so PT will be equal to summation of PI, right? So PI means, so I is 1 to n. So we can mathematically represent total pressure using partial fractions, right? So here we will be deeply studying about partial fraction, right? So as I told you, in the equilibrium constant equation, in the first equation we will be having pressure the concentration components, right? And here we will be having partial pressures in the equation, right? So we are going to study some equations, that's all, right? So now we will first look at Le Chatelier's principle, right? So in your syllabus, yeah, okay. Right, now I will explain you Le Chatelier's principle. Right, so now we are going to study the qualitative analysis of equilibrium, right? So the heading will be qualitative analysis for chemical equilibrium. Right, so a scientist called Le Chatelier came up with this idea, right? So what he told is, now you see in a chemical reaction, let's say this is a chemical reaction. Now if you increase the concentration of A, what will happen is the system will tend to reduce the concentration of A, right? So if you externally increase the concentration of A, the system by default or automatically will tend to, or the equilibrium will move in the direction in which A will be reduced, right? So let's say in the system we have A and B, right? So let's say here A is there, B is there, right? Okay, in the reaction system we have both A and B. That's why it is in equilibrium, right? What does it mean? In an equilibrium reaction we will be having both reactants and products. But in a, okay, for example, if you have something like this, so initially we will be have A, we will not have B. After the completion of the reaction we will be having only B, we will not have A, right? So this is for irreversible reaction, but the situation is different for reversible reaction. We will be having both reactants and products. Can you understand that?
Yeah.
Okay, so now you just see this. Now let's say you externally put some more A, we put some more A. So what will happen, the system by default or automatically will tend to reduce A. So if you are increasing A, what should happen? A should be converted to B. So in which direction will the equilibrium move? The equilibrium will move in the forward direction. Can you understand that?
Yeah.
Okay, and let's say we take some A out, we take some A out, right? So I'm going to write this way, right? So A is there, B is there. Now we take some A out. So what is happening to the concentration of A?
It is decreasing.
Now, if I take some A out of the system, so the concentration of
Oh,
A
it
is
will decrease.
decreasing, right? So the concentration of A is decreasing. So when the concentration of A is decreasing, what will happen? The system will move in the, or the equilibrium will move in the direction in which it will produce A. So now the A should be increased. So if the A should be increased, the equilibrium should move in the backward direction, then only B can produce A, right? So if the, can you understand this one?
Yeah.
Okay, now let's say we have, now these are the two situations, and another one, now A becomes B, right? Now if I increase B, right, so if I put some more A B to the solution, okay, now when you, I'm just taking a generic example, right? So after that I will tell you how you can predict these kind of trends using an example as well, right? So B, now if I increase B, what will happen? Will the equilibrium move in the backward direction or forward direction?
In the backward direction, right?
In the backward direction. Why? When we externally increase, the system should reduce B. So this should move in this direction. Then only B will convert to A. So automatically, because why? The balance should be kept, right? So if we increase B, then the number of A should be increased. Then only it will be in balance. Can you understand?
Yeah.
Okay, now again, if we have A becomes B, right? So now if I reduce B, which means I'm just taking some B, right? If I'm taking some B out, what will happen?
If you take some B out, what's it called? It will shift in the forward direction.
In the forward direction, the equilibrium will move, right? Okay.
Yeah.
Right. So can you just write this down in your own words? How can I tell? Right. So you can just write this way, right? So you can write. So when, according to Le Chatelier's principle, when the concentration of a component is increased, the equilibrium will move in the direction so that the increased concentration will reduce. Can you understand that? So when the concentration of a component is increased, the equilibrium will move in the direction so that the increased concentration will reduce. So how can you draw? How can you pictorially represent it? So if we have A and B, now if I increase the concentration of B, what will happen? The equilibrium will move in this direction, in the forward direction, so the increased concentration will reduce now, right? So since it is moving in this forward direction, what will happen? Again, A will produce more B, so the equilibrium will be in balance, right? Okay. And again the vice versa also will be true. If the concentration of a component is decreased, the equilibrium will move in the direction so that the decreased concentration will increase, right? So you can just write this sentence and draw these pictures, right? These pictures you can just draw them. Finished?
Not yet. Okay, yeah, done.
Okay, so now you can observe a trend, right? So now you see here, when we increase the concentration of the reactant, the equilibrium will move in the forward direction, and when you increase the concentration of the product, the equilibrium will move in the backward direction. So you can remember this point also, right? So here, if you want, you can write this also, right? Note as note, when the concentration of reactants is increased, the equilibrium will move in the forward direction, right? For example, let's say we have A plus B gives you C, right? Now I am telling you, if I increase the concentration of B, how will the equilibrium move?
It will shift to the right in the forward
in the
reaction.
right direction, right? Okay, I'm supposed to draw like this. Okay, wait. It should be double arrow mark, okay?
Yeah.
Right. So if I increase the concentration of B, the equilibrium will move in the forward direction. So if I increase the concentration of reactant, the forward equilibrium will be playing, right? So we will be considering the forward equilibrium. Now the vice versa. The second point is, when the concentration of products is increased, the equilibrium will move in the backward direction, right? For example, I'm going to take the same example again. Okay, otherwise if I take like this, A decompose to B and C, right? Now if I increase the concentration of C, what will happen?
If you increase the C, it will shift towards the backward reaction.
It will shift to the backward direction. So can you write these 2 points also? These are very important.
This is all based on the Chatelier's principle, right?
Yeah, this is called Le Chatelier principle.
Yeah.
This is point 1, and now we will look at an example, right? So the famous example that we will be looking at is the second step reaction of contact method H2SO4 production, right? So we will be studying industrial and environmental chemistry, but as far as I cramped your notes, that is not included. I don't know when you will study that. Sometimes when you go to university you might study, okay? Okay. So this is just an equation, right? So let's say I already told you SO2 plus O2, right? So these are all gases, and this is an equilibrium reaction, right? So it will produce SO3 gas. Now what will happen? Now as raw materials we will be using sulfur and oxygen. So we will be producing SO2 and O2, right? So we will be producing more SO2 and O2. so that we can produce more SO3 in order to make SO3 react with H2O to produce H2O, right? So industrially we will be applying Le Chatelier's principle to predict what we have to do in order to produce more yields, right? So this is an application side of Le Chatelier principle. Okay, so what we have to do is, now this is a process where we make H2SO4. So the raw materials will be SN, oxygen, and H2O, right? So we first SNO2 will react together to produce SO2. So this is an irreversible reaction. This is an irreversible reaction. Now the produced SO2 will again react with O2 to produce SO3, right? So from the first reaction, now we are adding sulfur and oxygen, right? So what is happening? SO2 are produced more and more. So here the concentration of SO2 is increasing, right?
Yeah.
And we are applying, or we are bubbling a lot of oxygen gases also through the tube. So O2 gas is also increasing. So what will happen? The forward direction will be moving, right? So the equilibrium will be moving in the forward direction. So we can produce more SO3, and the produced SO3 will be again reacted with H2O and produce H2SO4, right? So we will be setting some industrial setups, and this is how we are going to produce SO3. So this is an application side, right? So here, when the concentration of SO2 and oxygen are increased, then what will happen? SO3 should be produced. So here, when the concentration of SO2 and oxygen gases are increases, what will happen? The equilibrium will move in the forward direction, and we are removing SO3 also. How do we remove SO3? Now SO3 is made reacted with H2O in order to produce H2SO4. Again, what is happening? SO2 plus O2, right? So now we are now making react with SO3. Now what is happening? The concentration of SO3 is reducing. Can you understand? Why? Because again the produced SO3 is making reacted with H2O, which means we are removing SO3. So when we remove SO3, again, in which direction the equation should move?
Should move towards the left.
Oh, toward the right. Why? Because when we
Oh, yeah, sorry, right, yeah.
yeah, right. So this is an application side, right? Okay. Right. So when we study industrial chemistry, we will need equilibrium also. Okay.
Yeah.
Right. We have some practicals also, but okay. When we do questions, if we require those practicals, we will study, right? So I will just overallly explain all the things that you need regarding this equilibrium, right?
Mm.
Right.
Okay.
Now we have completed the first part of Le Chatelier principle. Now we will see how temperature will affect this equilibrium using Le Chatelier principle. Okay. The next one is determining the. Right, so if you want, you can write this way. Second one, determining the role of temperature in equilibrium using Le Chatelier principle, right? So now here, when we want to analyze the role of temperature in equilibrium, we have to have these points, right? So we have already classified chemical equations into exothermic and endothermic, right? So exothermic reaction and endothermic reaction. Right. Now in exothermic reaction, okay, let's say we have an equation or we have a chemical reaction. Now if the chemical reaction is exothermic, what does it mean by exothermic? Energy is energy is released to the
system, not to the system, the surrounding.
So from the system, energy is released to the environment, right? So endothermic means energy is absorbed by the
absorbed
system
by
from
the
the.
system.
Okay, so now listen this. In exothermic reaction, if we increase the temperature, the equilibrium will move in the backward direction. Equilibrium will move in backward direction, right? And if the temperature is decreased, here if the temperature is increased, now if the temperature is decreased, what will happen? The equilibrium will move in the forward direction, right? So equilibrium will move in forward direction, right? And in endothermic reaction, now we have to check if we have to increase the temperature or decrease the temperature depending on our need, right? So if we want to produce more reactant in an exothermic reaction, then we have to increase the temperature. And in endothermic reaction, if we want more reactants, right, we have to increase the temperature, right? So here when we increase the temperature, what will happen? The equilibrium will move in the forward direction. Equilibrium will move in forward direction. And here when we decrease the temperature, equilibrium will move in backward direction, right? So what you should know is, you can just highlight these important points, right? So in exothermic reaction, if you increase the temperature, the equilibrium will move in the backward direction. So you can just remember this point. And then in endothermic reaction, the vice versa will happen when you increase the temperature, right? So if you remember these points, then you can, if you want to predict anything, you can just take a rough sheet and write down this down. Then you can easily go to the answer. You can just predict whether to increase the temperature or decrease the temperature, right? Now we will be doing some examples. So before that, can you just note it down? So in other words, we can write this in this way also. When we increase the temperature, if you want, you can write this way also. When we increase the temperature, if the reaction is endothermic, or if the reaction is exothermic, and if the reaction is endothermic, right? So what will happen? Now here the reaction, now we will indicate using double arrow mark, right? So when we increase the temperature, just try to understand this, right? Right, just try to understand this. Right, okay. Now when we increase the temperature, if it is exothermic reaction, in forward direction, in the backward direction, okay. Don't confuse with this, because sometimes you might confuse in the exam also. So right, so when we increase the temperature, if the chemical reaction is exothermic, what will happen? The equilibrium will move in the backward direction, right? In the backward direction. And if the when we increase the temperature, if the reaction is endothermic, in which direction will the equilibrium move? In the forward direction. Can you understand this? This is just summary of what we have already written. Green color. Okay. So here in backward direction and here in forward direction, right? So you can write this down also. So you can easily predict what will happen when we do questions, right? Done?
Yeah.
Right. Now we will do some examples. Okay. Right. So as I told you, right. So we are going to take the second step reaction of contact method sulfuric acid production. So examples. Right. Now the second step reaction is an exothermic reaction. So SO2 plus O2 gives SO3. Right. So this is an exothermic reaction. So delta H is equal to positive or negative. If this is an exothermic reaction, delta H is equal to positive or negative.
Exothermic is thing, product minus reaction, so it will be negative.
Negative, right? So delta
Yeah.
H is equal to less than 0. Less than 0. So now if I increase the temperature, right? So during this process, what we will do is we will increase the temperature. So if we heat the system, what will happen? Now our objective is to produce more SO3 because we need SO3 as the intermediate product in order to make it react with H2O to produce H2SO4, right? So we require more SO3 gases, right? So what we will do is we will increase the temperature. So when we increase the temperature, if the reaction is an exothermic reaction, in which direction will the equilibrium move?
If you increase it on the well, it's exothermic. So if you increase it, the equilibrium will move in the backwards, so towards
Backward
SO2 and O2.
So in the backward direction.
Backwards.
So increasing the temperature in this reaction will not make any sense because what will happen? We are getting the raw materials again and again, but we need products, right? So in this reaction, what we will have to do is we have to reduce the temperature as much as possible. But if we want to make SO2 and O2 react together, we have to heat it, but you cannot overheat it, right? If you overheat it, what will happen? We will return the raw materials back. So industrially we have to keep a specific temperature, right? Because without temperature SO2 and O2 cannot, there are some problems, right? Practical problems are there. So without heating the system we cannot produce SO3, and if you overheat it, what will happen? Again the raw materials will be returned. So we have to keep a specific temperature, right? So that's why in industrial processes for every reactions we have specific temperature range, right? We will study them later for each reaction, right? So but now again if we have SO2 plus O2, right, again SO3, now if I reduce the temperature, what will happen?
If you reduce the temperature, it will shift towards the right,
Yeah, it will shift
so
to
towards
the
SO4.
right. Now again, if I take another example, let's say decomposition of N2O4, right? So N2O4 will decompose a NO2 to NO2. Now this is an endothermic reaction, right? So if it is an endothermic reaction, delta H is greater than 0. Now if I increase the temperature here, what will happen? The reaction will, the equilibrium will move in the forward direction, right? So can you write these two examples, these three examples below this? Okay, right. So the third factor that the equilibrium is affected is pressure, right? Now we have to analyze how the pressure will be changed using this Le Chatelier principle, right? So the third one is predicting the change of pressure. If you want predicting, am I audible?
Yeah.
Predicting the change of pressure in equilibrium using Le Chatelier principle. Okay, right. Now here you see there are points, right? So the first point, the theory is when we increase the temperature, the equilibrium the equilibrium will move in the direction in which we have less number of stoichiometric numbers, right? So here if I take an example, I am going to take the same example, right? So SO2 plus O2 gives you SO3 gas, right? So now what we have is when we increase the pressure, we don't want to bother whether the reaction is exothermic or endothermic. Now we have to count the number of moles of each reactant and products, right? So first, for that, what we have to do, we have to first balance the equation, right? So if you balance the equation, how can you balance this equation? Since we have an odd number of oxygen in the product side, we have to multiply it by 2, right? So now we have 2 sulfurs, so here we will put 2, and here we have 6 oxygen, and here we are supposed to put 3, right? Now the total number of molecules, or the what do you call, the stoichiometry mole number of the reactant side is 5, right?
Yeah.
Oh, is it okay? Yeah, okay. And here the stoichiometric mole number of product is 2, right? So when you increase the pressure, right? So when pressure is increased, the theory says, the Le Chatelier told that the equilibrium will move in the direction in which okay, right? Can you hear me now?
Yeah.
Okay.
Why are the oxygens not balanced?
I'm sorry?
Do you need to balance this or no?
Oh, I'm sorry. Yeah, I'm sorry, I made a mistake here, okay? Right, so here it is supposed to be 1, right? Yeah. Right, so here this is supposed to be 1, right? Because we have 6 oxygen in the product side, so we have already 4 oxygen in the SO2 and only 2 is remaining, so we are supposed to put 1 here, right? So the total number of moles in the reactant side is 3, right? 3. And the total number of moles in the 3, how do we obtain 3? This 2 plus this 1 is equal to 3. 2 plus 1 is equal to 3. And here we have 2. So when the pressure is increased, the equilibrium will move in the direction in which we have less number of moles, right? So when the pressure is increased, the equilibrium will move in the direction in which we have less number of stoichiometry moles, right? Okay, now here 3, here 2, so which is less?
2.
2 is less, right? So here the equilibrium should move in the forward direction, right? Because the reactant side has less number of stoichiometry moles. So when the pressure is increased, the equilibrium will move in the direction in which we have less number of moles. So when the pressure is increased in this reaction, the equilibrium will move in the right direction, right? And we will do another example also. So let's say we have nitrogen N2 plus H2. What will be the product? If nitrogen and hydrogen react together, ammonia will be produced, ammonia, right? And we have to balance the equation when we analyze the change of pressure. So here we will multiply this by 2. So here we have 2 nitrogen house, so no worries. And here 3, so this is supposed to be 3, right? Now, what will happen when I decrease the pressure? Can you just predict it?
So it will move in that direction where you have the greater number of moles.
Yeah, we have more number of moles. Yeah. So here in the
left side, so towards the nitrogen and hydrogen.
Yeah, so it will move in the backward direction. Why? Because we have 4 here, here we have 2. So when the pressure is decreased, the vice versa, right? So the equilibrium will move in the direction and we have more number of stoichiometric moles. So it will move in this direction, right? Okay. Right? So that's all about the Le Chatelier principle. We have discussed 3 things, right? So how the equilibrium will move when the concentration is increased. Then we studied how the equilibrium will move, or how the equilibrium will behave when the temperature is increased or the temperature is altered. And finally we studied how the equilibrium will behave when the pressure is altered, right? Okay, so now we will move to the quantitative analysis of equilibrium, right? So do you have any questions to ask regarding this qualitative analysis of equilibrium using Le Chatelier principle?
Not yet.
Okay, so now we will move to the quantitative analysis of so equilibrium concepts, Le Chatelier principle, KCKQ, then we will move to KSP also. Right, so you can see what factors affect equilibrium and how, right? So what are the factors affecting equilibrium? They are pressure, they are concentration and temperature, right? And how we have studied using Le Chatelier principle, right? So you can just go through it, right? So for your extra knowledge, and these are the summaries, and you can just take these notes as your summary. Right, Le Chatelier principle. Right, now you can see this, right? So here you should know the color of these components also. What is the color of NO2 gas? NO2 gas is a brown color gas, and N2O4 is colorless, right? So the name is nitrogen dioxide. The name of NO2 gas is nitrogen dioxide, and the color of this gas is brown color. And N2O4 is dinitrogen tetraoxide. How do we call dinitrogen tetraoxide? You see N2O4, right? So 2 means di, dinitrogen, and 4 means tetra. So we have 2 nitrogen and 4 oxygen. So we will call this as dinitrogen tetraoxide, Very simple, right? Okay, and this is colorless, right? Now right, so we have already studied. So if pressure is increased, right? So for example, here you see volume. So volume effect is also same as the pressure effect, right? So why? Because PV is equal to nRT, right? So here you see now volume effect, right? So the temperature, when the temperature is kept constant, now R is already a constant, right? So the number of moles will not change, right? So we can tell when the pressure, right? So the inverse method of we have studied already pressure, right? So what did we study? When the pressure is increased, the equilibrium will move in the direction in which we have less number of moles. But if pressure is increased, what will happen? The volume, right? So the opposite theory will be applied for the volume also, right? That is the case, right? Anyhow, when we do the questions, we will see, right? So we have already studied pressure, concentration, and temperature. You should keep these 3 points in mind, and right? So depending on the situation, we will see, right? So for example, let's say PV is equal to nRT. Now we have already studied how the temperature will behave with respect to equilibrium, right? So if the pressure is not changing, we can tell that the change in temperature will be applied for the change in volume also. Can we tell like that? Can we tell like that? Now, okay, so for example, we have already studied this equation. PV is equal to nRT. And we haven't studied any theory for volume, right? We haven't studied how the equilibrium will behave when the volume is changed. Have we studied? Yes. Have we studied yet?
No.
No, but we have studied for temperature change, right? So in the question we have to check if the factors are keeping constant. For example, if the pressure is kept constant, now we can tell that the change in temperature will be the change in volume, because they are directly proportional, right? So whatever the change, right? So if the temperature is increased, what will happen to the volume? So whatever the changes that we make for temperature will be applied for volume also, right? Can you understand that? Can you understand that?
Yeah.
Okay, right. So when we do questions, we will learn it, right? Okay, no worries, because these are the theories that we have for Le Chatelier principle, but we have to look at the questions to get some more understandings, right? Okay, after completing this unit, we will be having some paper discussions also, right? So first we will complete this one.
Okay.
Right, now we will move to the quantitative analysis, right? Okay. Right, so now right, so okay, so we haven't completed kinetics, right? So you will require kinetic knowledge also. Okay, right, so now what we will be doing is, for example, before coming to quantitative analysis of equilibrium, we should have some knowledge regarding this chemical kinetics, right? So chemical kinetics. Right. So I'm not going to talk much about this chemical kinetics. I will just introduce some important things that you should know in chemical kinetics, right? So in chemical kinetics, we basically study about rate of reaction, right? So the rate of reaction will be equal to K into, we can say, how can I explain it to you? I don't know. Okay, so you just understand, right? So rate will be equal to, we have an equation, right? So in chemistry, no, almost in science we have equations, and for equations we have some conditions, and when we meet those conditions, we can apply the equations in the given context, right? So this is what we are going to study here. Nothing is new here, or nothing is difficult, right? So we have an equation for rate. So to determine rate, we have to find out the concentration of reactants, right? Reactants, and we will be having something called N. So this is called the order of reaction. What is this? Order of reaction. Right. For example, let's say we have an equation like this, right? So I'm going to take A becomes P, right? So let's say this is rate. Here we will be having only one rate, because this is an irreversible reaction, right? Basically in chemical kinetics we study about irreversible reaction. So if I want to determine the rate of this reaction, I can write this as R is equal to K. K is what? That is the equilibrium constant, right? That is what? Equilibrium constant. That is what? Equilibrium constant. And this is A, right? What is reactant here? A into N, right? A into N. So since this is an elementary reaction, that will be exactly equal to, the order of reaction will be exactly equal to the stoichiometric ratio. So this will be equal to K into concentration of A, right? So now with this idea, we are going to transform this equation, or we are going to apply this equation for a reversible reaction, right? So let's assume we have an equation something like this. A plus B gives me C plus D, right? C plus D. C plus D. Now I am going to call this as RF and this as RB. What is this? RF means forward direction, and I can call this as RR, right? So RR means reverse reaction rate. Can you understand this? So we have a reversible chemical reaction where A plus B and react together to produce C and D. But in the system we will be having all these four species in the equilibrium, and we know since this is in equilibrium, RF should be equal to RR. Can you understand that?
Yeah.
Okay. Now we have this equation, right? We have this equation. Now I can write this as this, right? So if I take the forward direction, A plus B give me C plus D, right? Okay. For this reaction, if I write rate law, R forward is equal to Kf, right? So this is the equilibrium constant for forward direction, and I can write this way, A into B. Why? Because Rf is equal to what? The concentration of reactants. Now if we have more than one reactants, now we have to multiply each concentration. Right? We should have already studied chemical kinetics in order to thoroughly understand it. But anyhow, I will try my level best to explain this, right? Okay.
Okay.
what I have done is I have taken a reversible reaction where we have RF as the forward reaction rate and RR as the reverse reaction rate, right? Now at equilibrium, we know this is what we studied at the beginning, right? At equilibrium, RF should be equal to RF, right? Now if I consider the forward reaction, now RF is equal to KF into A plus B. Do you agree with this?
Yeah.
Okay. Now if I consider the backward direction, what is the reactants? What are the reactants in the backward direction? C plus D, right? C plus D give me A plus B, right? A plus B. So this is forward reaction and this is backward reaction, right? Now can you just try to write the rate law of this backward reaction? So how can you write it? Can you
The
just
what,
try?
sorry?
Yeah, okay, as I have written the forward rate law for the forward reaction, can you just try to write down the rate law of the backward reaction?
Is it KR concentration of C, concentration of D?
Yeah, so R will be equal to KR, right? KR is what? That is the what do you call equilibrium constant for reverse reaction, right? So otherwise you can say order of reaction also, right? That is a constant, right? That is a constant because we
Yeah.
call rate, this is called, we have something called rate of law of rate or rate law, right? So rate law tells that the rate is proportional to the concentration of the reactants, and if it is an elementary reaction it will be having n as order of reaction. Now if I want to convert this inequality or this proportional relationship to equation, now I have to multiply by a constant, right? So rate is equal to K into concentration of reactants into N. So this K is called equilibrium constant, right? So for the forward direction, equilibrium constant is KF, this one, and for backward direction that is something different, that is called KR, again C into D, right? Okay, now I'm going to take this equation as first equation and this equation as second equation, and I'm going to divide the first equation by the second equation, right? So if I divide first by second, I will get KC, right? Okay. If I divide the first equation by the second equation, what will I get? Can you just try to write it? So RF divided by RR is equal to KF divided by KR, right? KR into A into B now if I write this way you can easily understand, okay? If I write this way you can easily understand, right? Now if I divide the second equation by the first equation, right? If I divide the second equation by the first equation, how can I write? How can I write? RR divided by RF is equal to, I have to divide this portion by this portion, right? So KR into concentration of C into concentration of D divided by KF into concentration of A into concentration of F, right? Now theoretically the ratio between RR and RF is called KC, right? So KC is equal to KR divided by KF, right?
Yeah.
if you write like this also, that is also okay. Right, now listen, at equilibrium, what is the condition? Rf is equal to Rr, right? At equilibrium, otherwise if I explain this way you can easily understand. Okay, forget everything. Okay, right, so no need to divide this by this, right?
Okay.
Right, now you see here Rf is equal to Rr, right? So Rf is equal to Rr at equilibrium. Now instead of Rf, can I replace this? Can I replace this?
Yeah.
Okay, so Kf into concentration of A into concentration of B, right? Concentration of B. That will be equal to, can I plug in Rr using this expression? The second expression, Kr into square root of, the concentration of C into concentration of D, right? So I am going to rearrange the concentration one side and the constant in one side, right? So I bring this Kr to the denominator of the Kf, right? So Kf divided by Kr is equal to concentration of C into concentration of D divided by concentration of A divided by concentration of B. Can I write this way?
Yeah.
Okay. Right. So now you see this Kf is a constant, right? Again Kr is a constant. Constant means it is a fixed value, right? So we are going to denote, or we are going to assign a value for this constant as Kc, right? So
Okay.
Kc is equal to concentration of C into concentration of D divided by concentration of A into concentration of B, right? So this Kc is called the equilibrium constant. Have you understood this?
Yeah. Okay.
Right, so let me explain it to you again, right? So we took an example for a reversible reaction where we had A and B as the reactants and C and D as the products, right? So at equilibrium we know that Rf is equal to Rr, which means the forward reaction rate should be equal to backward reaction rate. Then we considered the separate forward reaction and the backward reaction, and we wrote low rate for both reactions, and then we equated the Rf and Rr and obtained this expression, right? And then we assigned this fraction as Kc, that is the equilibrium constant. So which means Kc, right? So the equilibrium constant with respect to, or associated with concentration, right? Concentration will be equal to concentration of C into concentration of D into divided by concentration of A divided by concentration of B. Now understand this. This portion is the concentration of products, right? Concentration of products, and this portion is the concentration of reactants, right? Right. Now we will be doing some examples, and if we have stoichiometric ratio, why? Because in the equation we took, we have 1, 1, 1, 1, right? So the exponent of this concentration is also 1, 1, 1, 1, right? But if we have a generic equation like this, AA plus BB becomes CC plus DD. Now Kc will be equal to the concentration of C, and the stoichiometric ratio or the coefficient will become the exponent of the concentration, C power C into D divided by concentration of A into concentration of B into B, right? So this is the equation that you should remember, right? So this is the equation that you should remember. And this is the proof, right? So if they ask to prove this expression in the exam, you have to follow this method, and this is the generic equation, right? So can you just write this down, or else can you just take the screenshot? Have you understood this equation? So how are you going to write Kc? You have to put the concentration of the products in the numerator along with the coefficient as its exponent, and in the denominator we have to put the concentration of the reactants and with the exponent as their coefficients. Have you understood? This is how you have to write the expression for Kc. Now I am going to give you an example. We are going to take our typical example where we take the second step reaction for the HCS of that one, right? SO2 plus this equation. I don't want to introduce this equation more and more. O2 gives me SO3, right? So now can you just try to write the Kc expression for this reaction?
The Kc expression?
Yeah, Kc is equal to?
If it's at equilibrium, you didn't have to put the...
You don't need to prove it, right? So you can directly write down the equation.
I need also really quickly for the 2, it's like, I forgot to bring my thing that I normally use it for. I just write it. So that's 2 there, and then there's a 1 here, and then there's a 2 here, there's a 2 here. Okay. Yes, okay, you are correct. So first you have to balance the chemical equation, and then you can simply write down, right? So after that, yeah, right, that's correct. Okay, fine. So again, now I will give you some example questions. You can come with the answer in the next class, right? And we will now wind up, right? So question is, write down the expressions for the following expression for Kc for the following equation, right? So the first equation is N2 plus H2 gives me NH3, and the second one is carbon plus H2O, right? So if carbon reacts with H2O, what will be the product? Now let's say this is incomplete reaction, right? So let's say we have CO and H2 gas, right? CO gas and H2 gas, right? So this is a solid, and here this is a liquid, right? And one more thing you have to consider, that when we, okay, now you see, for solid substances, do we define the term concentration? Do we find concentration for solid substances? No, we don't.
No. we define concentration only for liquid and gases. So if we have any reactant or product in the solid phase, we will not involve them in the expression of Kc, right? So that point is also you should bear in mind. So here in the expression of the second equation, we will not involve concentration of carbon because this is in solid state, right? So we will look at why in the next class. And third one is calcium carbonate decompose as calcium oxide plus CO2 gas. So for these three reactions, you can write down the expressions for Kc and come with the answers in the next class. And since I am also in vacation, we can schedule sessions throughout next week starting from tomorrow if you are free at this time, at the same time, if you agree to have sessions from 10 to 12.
I'll try, but I'm still in Melbourne right now,
Okay.
and I'll be back in Sydney on Thursday.
Thursday.
Yeah, so I'll update you hopefully by Wednesday on whether I can do a class on Thursday. Or
Okay, so till
Thursday or
Thursday you
Friday.
don't need to, I don't need to schedule any sessions for you, right?
No, it's
Okay.
okay. Yeah.
Okay, then fine. And if you are, even if you are in Melbourne, no worries. If you can attend sessions, you can inform me. We can, as you requested me earlier, we can schedule sessions at most time. Okay.
Yeah. Yeah.
Okay. Anyhow,
Yeah.
you can update me the time. We will meet in the next session.
Yeah.
Okay.
Yeah. Thank you.
Okay.